Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we did talk about a magnetic force, and we said, for example, if a magnetic force, or let's say if a charge moves into a magnetic field, of course it experiences a magnetic force in that case. And if you do remember, we said a magnetic force on a charge would equal to QVB sine theta. And of course, in order to get the maximum force, the particle or the charged particle has to go into the magnetic field perpendicularly. And of course we did say, we did use the equation to find the magnitude of the magnetic force on the charge. And of course, in order for the direction, we used the right hand rule in order to tell the direction. And of course we said we're going to use the right hand rule, but make sure that you have a pen or pencil in your hand. Of course, the tip of the pen, or you can say the palm of your hand, basically represents the direction of the magnetic force on a positive charge, and the back of your hand would represent the magnetic force on an electron here, or you can say on a negative charge, you can say. So we said the thumb basically represents the direction of the motion, or the velocity. In this case, your fingers would represent the direction of the magnetic field, and then the palm or the back of your hand represents the direction of a force, either on a proton or a positive charge, basically, or on a negative charge. Okay, and then we ended up at this point right here. Question 10 says, that is chapter review question, by the way. It says two charged particles are projected into a region where there is a magnetic field, as you can see, for example, here, but perpendicularly, obviously, these two charges will go to their velocities. If the particles are deflected in opposite directions, what can you say about them here? Okay, so basically that is what we have, yeah? So consider that it doesn't say whether the charges are positive or negative, or which one of them is positive, which one is negative. It just tells you that when these two particles are moving into a magnetic field, they deflect, they shift in opposite direction, or they move, or simply they move in opposite direction. So what can we say about their charges? Now, in order to understand this, consider one of the charges only. For example, let's talk about a positive charge. Let's say one of these charges that is going into magnetic field is a proton, let's say. So what happens if that is the case? Remember, using the right hand rule, remember this, the direction of the motion, the magnetic field, then this would be, because we have a proton, so this is going to be the direction of the force on this proton, or the magnetic force, you can say here. So watch this, crosses, that means the magnetic field is into, basically, if that is the page here. So if that is the case here, going into, and this is the direction of the motion, so just focus on the positive charge here, you can see that it will encounter or experience a force which is upward, basically. So we can tell, or based on this, we can say that a proton will experience a positive force on it, and this force, of course, is going to be upward, you can say, okay, or it is going to deflect upward for proton. But if the other charge, or let's say we don't know the type of the other charge, if it is going to deflect the other way, that means it has to be opposite to this, because remember, we said that, let's say if the proton is moving to one side, if it is electron, the force will be, you can say in the opposite direction here, or you can say if it is an electron, it will be just the reflection of the proton here. So if this is the proton, this is the reflection of, you can say if this is the direction of the force on a proton, or the path of a proton, this is the path, or you can say the reflection of this one, that is basically the path of an electron, you can say, or you can say the force basically would be in opposite direction. And of course, if they're deflecting in opposite direction, so the forces must be in opposite direction, that means the charges must be opposite. So we can say they must have opposite charges here. Okay, for question 11 says, suppose an electron is chasing a proton up this page. Okay, so I want you to focus or think of this, let's say, as a page here. So in order to emphasize on this, we can say, consider that this is, let's say, the page, okay? This is what we have. So this is basically up, and of course this is, you can say, down here, and this is the right side, and this is the left side of the page as well. Okay, so an electron is chasing a proton up this page when suddenly a magnetic field pointing into the page is applied, what would happen to the particles? We said that, for example, whenever we have two opposite charges, of course, their path will be the reflection of, let's say, of their reflections, you can say, or the path of one will be the reflection of the path of the other one. If not, just use, let's say, the right-hand rule. Of course, you don't face any of these troubles anymore. Okay, or you don't have to worry about this here. So let's say that this is basically a proton. So up the page, so that is the direction here, and of course the magnetic field is into the page, as you can see, yeah? So pointing into the page. So the proton, you can say, moving upward, okay, that is, if this is the page, here is the motion upward, an electron is chasing this proton here. So we could write the electron here, but for simplicity, we've done it here. That is basically the same thing. So if that is the case, what would be the direction of the magnetic force on this proton? So remember this, upward, you can just align your hand just like the same way that is shown here. So this is the direction of the motion. Remember the thumb, yeah? Okay, so the thumb would be the direction of the motion. Your fingers, the direction of the magnetic field. So the palm basically would be the direction of a magnetic force on a positive charge. So if proton is moving like this, of course it would get a force into this direction. So you can see that the proton will no longer continue on a straight line because it is there is a magnetic force on it. So this magnetic force, of course, is going to change the direction of its motion. Okay, remember this. What about if it is an electron here? Yeah, so you can do the same thing here with the electron, but we said this side, the palm for the positive, the back of the hand for negative. Yeah, so you can see here, if that is the case, an electron would get a negative, or let's say a force to the right side in this case, of course. So it's not going to move straight; it is going to shift, or you can say move or bend to the right side here. So this would be for electron, and of course this would be for the proton. So this is what happens when these two are moving up the page and they encounter or experience a magnetic field here. Okay, and this is basically the old TV generation, you can say. And of course they used to direct a beam of electron onto the screen so that they can show you an image. This is, of course, we're not focusing on this, but I've told you this for a reason, or for this question you can say here. Okay, and that is basically question 12 here. It says, why does the picture on a television screen become distorted when a magnet brought near the screen? So you do know that, even if you don't have the screen or you don't know about these type of screens, basically, let's say we have, let's just say we have a beam of an electron, okay? Let's use this. Okay, so we do have a beam of electron. Okay. We can move this one a little bit to the side as well. Okay, so we do have a beam of electron, let's say. So here's a beam of electron, a bunch of electrons all moving together. So what do you think will happen when there is a magnet brought near to this? Let's say here is a magnet, yeah? This is north and south. What do you think will happen when this happens? Of course, you can see this. Let's say this is normally the path of, let's use this. Okay, so this is normally the path of the electrons, okay? And then this is basically the direction of the magnetic field. You do know that magnetic field lines are going from north to south, yeah? So you can see here, if I draw this one more time, let's say electrons are moving this way, and there is a magnetic field which is at right angle to this, let's just say. So what happens, or what do you think will happen to this? So let's say there's a magnetic force. So what do you think will happen to this? And of course now, you can say the direction of these the direction of the motion of these electrons will change. That is because now, not a magnetic force, by the way, this is a magnetic field, okay? This is a magnetic field, of course. This, they will experience or encounter a magnetic force, which makes them change their direction here. So if, for example, let's say, remember that is an electron, yeah? So here is the direction, you can say, of the direction of the magnetic field here, but this is the direction of the motion you can see here, yeah? So if we assume that this is the direction of the magnetic field, let's say it is upward, and the direction of the motion, it is on x-axis, let's say. So if that is the case, remember, we're talking about electrons, yeah? So the back of your hand. So the electrons will get a magnetic force, basically, that is into the page, which in this case, of course, it makes them move, let's say, or bend or change their direction. And of course, this magnetic force will shift or make these electrons to change their direction. And of course, if these electrons are changing the direction, they're not going to fall on the screen here. And if they don't fall on the screen, and of course, the image, you can say, the image will be distorted. We cannot say there will be no image. It's just like the image will not be clear anymore, okay? Because the image will be ruined, you can say. Okay, so that'll be the case for that. Okay, take a look at question 13 as well. It says a proton is moving horizontally, yes? Horizontally enters a region where there is a magnetic or uniform magnetic field, you can say, perpendicular to the proton's velocity. As shown below, you can see here. Describe the path of the, describe the proton's subsequent motion, and how would an electron behave under the same circumstances? So take a look here as well. Now, you can see there is a proton which is out of the magnetic field. What happens when it enters the magnetic field? And then, for example, what happens when it is inside the magnetic field, or how does it behave in this case? So now, in order to do this, of course, you'll need to use your right-hand rule so that you can tell what happens inside the magnetic field. So if that is the case, remember to use the right-hand rule, okay? So the palm, the force or magnetic force on a positive charge, the thumb, the direction of the velocity or motion, you can say, and of course the fingers would represent the direction of the magnetic field. So the magnetic field is into the page, so that is one, and you can see this is, I'll have to do this way so that I can align my hand the same way that the proton is moving. So if that is the case here, once it is right here, you can see that it will experience a force which is upward here. So we can say when this proton is inside the magnetic field, it will experience a force which is upward here. Let's use this one here. So it will experience a force which is upward. That is the case here. So in this case, of course, this particle will move in the direction of the force, you can say. So let's assume that the particle is here at this point, okay? So if that is the case, you can see this will be the direction of the motion, which is upward now, let's say velocity, and remember the direction of the magnetic field, it is still into the page, we can say. So if that is the case, we can do this one more time here. So let's say at this point here, we could do this, by the way, just stay with me for now. I'll tell you something about this one here. So that is the initial path, you can say. If that is the case, the proton is moving this way, it will experience a force upward. So that is the case, then of course the proton will be moving upward if that is the case. So at this point here, you can see when the proton is moving upward, you can say, or up the page, but this time you can see the force will be basically moving into this direction here. If I draw it, let's say, a little bit up here, you can see that we can say the force, in this case, it is into this direction here. And of course, if that is the case, you can say it will be, once it is moving, of course, it gets out of the magnetic field. Once it is out of the magnetic field, of course, now it can continue on, it is straight line, or you can say it will move in a straight path. So, but you can see here, this movement, it is not going to move, for example, horizontally and then directly upward. Now, the turning, it is not that sudden, okay, because it is a magnetic force. So of course, this turn, we can say it is going to bend like this, and of course after this, and this is what happens here. So you can see that if I erase this one here, so this motion or the turning is going to be smoother rather than, let's just say, that is going, let's say, horizontally, then vertically, then horizontally again. It's not going to be like this. It is going to be somewhat smoother than this. So it's going to be something like this, for example, yeah? And this is until it goes out of the magnetic field. So if that is the force on a proton, on a positive charge, how about an electron? What happens if there is an electron there? And of course, the electron would shift or change the direction in the opposite way, okay? So if this is, you can say, half a circle, but this half a circle is counterclockwise for proton. If it is counterclockwise for proton, so guess what would be the direction for an electron? That is going to be clockwise in this case, you can say. So, but watch this, yeah? Does it complete, for example, does it complete the circle? No, it is just half a circle, then it walks out of the magnetic field, and of course then it continues in a straight line if I extend this line right here. So you can see that the proton curves upward and then makes half a circle and then moves out of the magnetic field, and then it's going to be parallel. It is going to be parallel to the original path, you can see. So these two are basically parallel. It is going to be the same thing with an electron, but the only thing that is different is the force is basically upward here. This one is the force is going to be downward here. At this point, the force is going to be this way here. So of course, you can see that it makes, for both, it makes half a circle, but one of them is going to be counterclockwise. The other one is going to be clockwise. Okay. We have question 16 says, at a given instant, a proton moves in the positive x direction in a region where there is a magnetic field in the negative z direction. what is the direction of the magnetic force? Does the proton continue to move along the x-axis? Of course, the answer is not. So one more time, take a look here. So we have where the proton moves in the you can say in x-axis or positive x-axis. The magnetic field is into the negative z-axis. So perhaps we can draw this one here as well. I'll draw it upward here. So watch this. Negative z-axis, that is basically, that means into the page, correct? Into the page. And the proton is moving, let's say, in the positive x-axis. So here is, let's say, a proton moving in this direction. And you can see this is basically the direction of B, which is negative z direction into the page, you can say. So if that is the case, how would this proton, let's say, behave once it is inside the magnetic field, let's say? So let's add one more raw here. Okay, so take a look. If that is the case, what happens? Let's just assume that, take a look here. What happens, yeah? If that is the case, use the right-hand rule, yes? So there's the direction of the motion, okay? And then the magnetic field is into the page. So what would be the force once it is inside the magnetic field, let's say? So if that is the case, it is trying to go horizontal, but magnetic force doesn't allow it, so it is going to change its direction. One more time. So at a point here, the magnetic force is going to be upward here. Okay, once it is moving upward, you can see, let's extend this one a little bit here. So if that is the case, watch this. Into, that is the magnetic field, okay, the direction of the magnetic field, this is the direction of the motion. So what will be the force on the proton when the proton is here? So here's when the proton at this point, here's when the proton is this point. You can see that the force is going to be in this direction, yeah? So of course this proton is going to change its direction. But what about the force on the proton once it is at this point here? Okay, so when it is at this point, take a look one more time. So this is the direction of the magnetic field and this is the direction of the motion. So the force is going to be downward. So of course, in this case, here is the force downward on this. But like I've mentioned earlier, these change in direction are not going to be this sudden or this sharp turns. Yeah, of course, it's going to be smoother. So instead of this, we can draw something like this. So here's how the direction or the proton will move inside a magnetic field. So you can see here, the proton will move counterclockwise inside the magnetic field. So this is basically what happens. So we can say the direction of the magnetic force will be along the, by the way. So at this point here, when it is here, the direction of the magnetic force is going to be along the positive y-axis here, yeah? Once it is here, you can say it is going to be along the negative x-axis here. Here, negative y-axis. Here, positive x-axis. So until it makes a full, complete cycle here. But I want you to remember one thing very carefully here. So we have a magnetic field. We can use the table to determine the direction of all this as well. Remember, we have a magnetic field. We have the direction of the velocity. So we can easily determine or tell the direction of the magnetic force on this proton as well. So you can see here, this is negative z, this is positive x. So the other axis is going to be y-axis, but remember, is it going to be y positive or negative? That is basically what you need to know by using your right-hand rule. But remember, this table will only work when the proton is at this point here. Once it is here, of course, things will change because the direction of the motion here is on y-axis, so no longer on positive x-axis anymore. So, but you can use this table for every part here, for example, here and then here and then here as well. So you can, until you make a complete or full circle over there. And this is basically how you can tell. So the direction of the force is going to be on positive y-axis. That is the first place, guys. So you can see here that it is, then after it is moving, for example, horizontal, it is going to move, let's say, vertically here. So this is what happened. But something else which is also very important, you need to know that this motion right here, it is only in the plane of xy axis here because the magnetic field is in the z direction. So this, you can say, motion is only going to be on, you can say, in the plane of x and y axis only. Okay, so what happens over there? You can see the direction of the magnetic force will be along the y axis. All right, then what is the other part? Well, the direction of the magnetic, what is the direction? We said that. Does the proton continue to move along the x-axis? The answer is no, because once it is, for example, on y-axis right here, it will, no, the question says, like, will it continue on the x-axis? Is it that? Okay, yes. So the answer to this question, no, because after, for example, it enters the magnetic field, it is going to move on y-axis, let's say. Will it stay on y-axis? No, because if there is a magnetic field, for example, or continuous magnetic field, you can see that this magnetic field will change its direction to, let's say, this direction here, let's say towards the x negative direction here, and then of course after that towards the y negative. So you can see here, at no point the proton is going to move in a straight line. So it will always encounter a force which makes it move in a circle here. So to answer the second part, does it continue to move along the x-axis? The answer is no, because the proton will move in a circle in the xy plane here. Okay, now we have another question. Take a look. These are very important as long as you know how to align your hand the same way that you're taught or you learned so far. If you don't know still how, try to practice these until you get used to these, and then of course it becomes so easy. So it says, that's question 17 says, for each situation below, use the movement of the positively charged particle and the direction of the magnetic force acting on it to find the direction of the magnetic field. So basically what we have here, we have two directions. You need to find the third one here. So we have, let's say, the magnetic force, we have the direction of the motion, and then you're required to find the direction of the magnetic field. So you can just use your right hand rule, that'll be it. If not, you can use the table that I've taught you. That will also help you to determine the direction as well. So, but remember, this 3 must be perpendicular to one another. So if I use a small table here, we have magnetic field, we can say direction of the motion, and the magnetic force as well. The direction of the motion is in positive x-axis, you can see here. Okay, and then the direction of the force, we can say it is on y-axis here. Okay, positive y-axis. So what is left for the magnetic field? It is going to be z direction, but is it positive or negative? That you need to use a right-hand rule in order to determine that. So basically, if that is the case, watch this. This is the direction of the motion, and this is the direction of the force, yes? If that is the case, then what is the direction of the magnetic field? It is into the page, yeah? If it is into the page, you can either say negative z, or you can say into the page, assuming that, let's say, this is the page, or we have coordinates, let's say x, y dimension. So you can use one of the two or both, that is both the same. So we can say into the page, yeah? Or you can say z negative, that is also correct if we use x and y, z direction here. Okay, now take a look at the second one here. It says, take a look. Remember, a point, that is the direction of the velocity or motion which is outward, out of the page. Or you can say z positive if you want to call it. The force is basically on y-axis, yeah? So let's use this one again, a table, okay? Once again, B, and then we have V, and then the force, yeah? So remember, the V is basically Z positive because it is out of the page, you can say. And then the force, again, positive y-axis. So for B, remember, we have z and y, so the other one, or B, has to be x-axis, but is it positive or negative? You need to use your right-hand rule for that. So in this case, remember this, I'll align my hand just like the same way that the direction tells me. If not, you can just look at this one or this gesture, you can say, and of course you can align your hand the same so that it can help you to tell what the direction is. So in this case, remember, we're talking about a positive force, so that is the tip of the pen or the palm of your hand here. So the direction of the motion is outward, that is towards you can say, out of the page, out of the board you can say, and then the force is upward. If that is the case, what is the direction of my fingers here? And of course that is towards what? Towards x-axis we said, but is it x positive or negative? That is of course x positive, so we can say x positive, yeah? Or to the right as well, if you're willing to call it right, left, up, down here as well, yeah? So once again, if I call this one, for example, up, and if I call this one out, then I can call this one right as well. So you can either call it to the right, or you can call it x positive as well. Okay, so this is the direction as well. So let's make this one more obvious here. So we can say, okay, let's just use x positive as well. What about the last one? Can you tell, what is the direction of the magnetic field in the last one? So once again, but remember, this time the motion, or the direction of the motion, is into the page, and the force is, you can say, to the right, so what will be the direction of the magnetic field? Once again, it is very important to be able how to align yourself the same way that the direction are telling you, yeah? So here, for example, V is into, so we can do something like this, yeah? But if I do this, watch this, the force is pointing the other direction here, so I don't have to do this, I'll have to flip it in this case, yeah? So that the force is in the same direction as this one here. So if that is the case, you can see V is into the page, the force is there, so I can tell that the magnetic field is basically towards the bottom of the page, yeah? If not, let me just move this one down a little bit so that I can align my hand better with this one here. So once again, take a look. This is into, right? Into, you can see my thumb here. That is into the page, okay? And then the force is to the right, to the left, by the way. So you can see either down or towards the bottom of the page. If you're given coordinate, you can say y negative as well. That is also fine, you can say, okay? So this would be what we have in this case, yeah? So you can use the table as well to tell the direction for this one as well. I hope you understood this one well enough. If not, please keep practicing until you learn how it is done. Now we have another question which is similar to this, but in this case, the force is not given. You need to find the force, let's say, on a positive charge as well. That is a proton, okay? So let's try this one as well. So take a look. The magnetic field is, remember to hold the pencil like this. So this is the tip. That is the force on a positive charge. Magnetic field in this direction of the motion here. So the motion is upward, you can see, and the direction of the magnetic force is magnetic field is into the page. So the force, of course, is going to be towards the left, you can say, yeah. And of course, if you're going to use x, y direction here, that is going to be y direction here. The direction of let me use this table again for this one here. So if we're going to use the direction or the coordinates x, y, z here, we have b, we have v, and of course we have. Let's erase and make this one nicer. Okay. So we have B, we have F, and of course we have B, V, and F as well, okay? That is magnetic field, motion, direction of the velocity, and then this is the force. So you can see that it is into the page, that is negative Z, okay? What about the direction of motion? It is positive Y. So as you can see here, we have Z and Y, so the third component, in order to be perpendicular to this, it has to be X direction. But is it positive or negative X, you need to use your hand, okay? So of course, once again, upward, that is the direction of the motion. Here's into the page, that is the direction of the magnetic field. So you can see the force is going to be on x-axis, okay? But it is going to be negative x-axis, yeah? If you are going to call it right-left, of course, it's going to be left of the page in this case, yeah? Considering this, for example, a page, let's say, or you can make it a little bit bigger here. So of course the force is going to be in this direction. That is the left side of the page, let's say. Okay, moving to the next one here. Take a look. That is also another easy one here. So we have magnetic field, which is, let's say, to the right in this case, okay? Or you can say towards x positive, yeah? So if that is the case, the motion is upward. So the magnetic force here, and this time, remember, that is the magnetic force on an electron, or negative, that is the magnetic force on a positive charge. So of course you can see that it is into the page, or you can say Z negative as well. That is also fine if you're using the coordinates. Okay, what about this one here? You can see, align your hand the same way, yeah? If I do this, watch this. If I do this, that is the same way as the direction of the magnetic field, but look, the velocity is pointing the other way, I'm pointing the opposite way, yeah? So I'll have to flip it, just like this one here. Now it makes more sense, yeah? That is the same direction as the magnetic field, you can say, and this direction of the motion. So the direction of the force on a positive charge, that is going to be out of the page, or you can say Z positive, that is also fine. Okay, what about this one here? You can also tell, remember, but this time the direction of the magnetic field is pointing towards you, that is out of the page, yeah? If that is the case, I'll have to align my hand like this, that is the magnetic field, which is outward. What about the direction of the motion? It is to the right, you can say, or x negative, that is also fine. And then what about the magnetic force here? Can I say it is upward? Yes. Or if it is, if you're not using upward, or the top of the page, you can say, let's say, you can use, let's say, y positive as well. That is also fine, because this is z positive, it is towards you, and this is, let's say, x negative, or to the left. So this one, it is either towards the top of the page, you can say, or you can say positive y as well. Okay, so you can say towards the top of the page, or positive y, that is also fine. Okay, so these are basically about the directions. I hope these are enough, and make sure that you are going to practice these without questions. Perhaps we can solve some together. So as according to the right-hand rule, what is the direction of the force on an electron, yeah? So we said if it is an electron, of course, the palm for positive, the back of the hand for negative, yeah? So which one says that? It says out of the palm of the hand, okay? Out of the palm, that is for positive proton. No. B, out of the back of the hand, that is the correct one, yeah? So the direction of the force is going to be out of the back of the hand, you can say. So, of course, the correct option here is going to be option B. Okay, what about part B or question 2? It says, if a positive charge is moving in the plane of the paper in a clockwise circular path, what is the direction of the magnetic field? Now, this is something very important, guys. Whenever it tells you that something is moving, let's say either clockwise or counterclockwise or even in a circle, okay? I want you to remember this one always. Whenever it tells you that a charge is moving either in clockwise or counterclockwise, I want you to do this, yeah? So here, let's move this one down. Let's get it back. I think we can all get it back here. Okay, I think we did move this one. All right, so I think I cannot move it anymore. Let's get this one back here. I was supposed to be... I hope you're not doing the same thing. Okay, so bear with me here. It says what? We're trying to do the second question. Whenever it tells you that a charge is moving clockwise or counterclockwise, so always remember this. Okay, so first of all, try to know what is the nature or what is the type of the charge. Here it says a positive charge, so this is very important, yeah? It is moving in the plane of the paper in a clockwise direction. This is clockwise direction, so 12, 3, 6, and 9, yeah? Okay, and of course it completes. So this is clockwise direction here. Okay, and it says it is a positive charge, yeah? So remember this, whenever a charge is moving in a circle or clockwise or counterclockwise, there is a magnetic force. It is always directed towards the center, always, okay? So I want you to remember this. So let's say at a point here, what is the direction of the motion here? The direction of the motion, we can say, is tangent to the circle. Or you can see that it is towards the right, yeah? So I can extend the line here. So I can call this one V. That is the motion or the direction of the motion of the positive charge, yeah? We said the direction of the force is always directed towards the center of the circle because that is basically centripetal force. Okay, whenever something moves in a circle, there must be a centripetal force. This centripetal force basically would be provided by the magnetic force. So we can say the direction of the magnetic force is towards the center of the circle. Now, you do know two directions here. So can you find the third direction? Yes, and that is pretty easy. So you can either use the table first, and then you can use the right-hand rule. If not, you could just use the right-hand rule, and that'll be fine. So let's use the table here. If we use the coordinates here, that is basically, let's say B, again V, and then magnetic force as well. So this extra. So this one we don't know. The direction of the motion is basically towards the x positive or positive x. The direction of the force, so we can say it is negative y at this point, by the way. We're talking about this point here. So can you tell or guess the direction of the magnetic field? And of course you should know. So basically we have two components here. So the third component must be y-axis here. But is it going to be, z-axis, okay? Because we have x and y. So the third component must be z-axis. But is it positive or negative? Then you have to use your right-hand rule here. So let's do this, yeah? So remember, we're doing this. This is the direction of the motion, correct? But the magnetic force is basically downward, so I'll have to do the opposite of this because this is the direction of the motion, the force is upward, so I'm not going to do this, yeah? I'll do this way here. So remember this, I'll have to align myself the same way that the direction tells me here. So this is the direction of the motion, this is the direction of the magnetic force. So what must be the direction of the magnetic field in this case? It is going to be in z-axis, as you can tell, but is it out of the page or into the page? It is out of the page, we can call it positive, yeah? So you can either call it z positive or you can call it out of the page as well. Out of the page. Out of the page. Now, what happens if instead of, let's say, a proton, let's say, we had a negative or an electron moving clockwise, yeah? You would do the same thing, of course. You can make it the table, then, of course, you can use the right-hand rule. But let's change the situation a little bit. Let's say that what happens if the direction of the motion were counterclockwise direction? What would happen if the direction of the motion were counterclockwise counterclockwise direction. If that is the case, then that means this two would be opposite, yeah? So in this case, of course, the direction of the motion is going to be this way, and this is where it is, yeah? So in this case, of course, here is going to be the direction of the motion, which is going to be negative x-axis. You can still, at this point, because it is moving at a circle, so still it is towards the circle, and that is basically towards, you can say, y negative, and then you can find the direction of, let's say, the magnetic field in this case. So we said for this one, for the first time, it was out of the page, or z positive. For this one, once we change the direction, it must be into the page. Let's just determine, and see if it is correct or not. Okay, so once again, align or use the pen like this, okay? So you can tell here that if this is the direction of the motion, as you can see here, the force is downward here, so the magnetic field must be into the page here. Okay, so I want you to try and tell me, for example, what happens if we use this with an electron here, yeah? So imagine if we have an electron, okay? This electron is moving in a clockwise direction here, clockwise, and of course, remember we have an electron, okay? So you tell me if that is basically electron moving clockwise, what would be the direction of the magnetic field, okay? So that is your homework, basically. Try to tell me what would be the answer in this case, okay? So use the same method, okay? Try to tell me what would be the direction of the magnetic field, and then try to do the reverse. What if it is counterclockwise the direction? Okay, counterclockwise. Okay, so in this case, which one was it? I think we didn't answer the question though. It says if a positive charge is moving in the plane, let's say plane of the paper in a clockwise circular path, what is the direction of the magnetic field? We said the magnetic field must be what? Must be out of the page, yes? So of course we can say option B would be correct in this case. Okay, what about question 3 here? It says in the figure to the right, what is the direction of the magnetic force on the proton moving inside a magnetic field? So this is very easy. If not, just align your hand like this and see what would be the direction, and of course you can do it yourself. Okay, now what about this one here? Because this one is we're basically using east-west and stuff, so let's do this one as well. It says an electron moving north encounters a uniform magnetic field. If the magnetic field points east, what is the direction of the magnetic force on an electron, guys? Don't forget. So we have an electron. Okay, so let's bring this one back here. So what do we have? We have basically an electron. We're trying to find the direction of what? The direction of magnetic force on an electron here. So how about we make a table first? Okay, so let's say this is a magnetic field motion, and this is the magnetic force on an electron as well. Okay, so it says an electron moving north, yeah? If that is the case, this is the direction of what? This is the direction of the motion, moving north. So this is north. It says a uniform magnetic field. The magnetic field points east. The magnetic field points east, yeah? So this is east. Remember the directions, correct? So we have north, south, east, and west. So watch this. We have east, we have north, so you have this two, yeah? So if that is the case, you have these two components, then the third component must be, it is either into or out of the page, let's say. Why? Because we have north and south. If that is the case, this is still considered horizontal, which is to this, we cannot use that. Okay, it's almost like if this is, for example, x positive, we cannot use x negative as well, because that is basically horizontal. So we're using horizontal and vertical components. So the other component that is left, it is either into or out of the page here. So if that is the case, remember, we're talking about an electron here, yeah? How about you align your hand the same way that it is, yeah? So we have the motion that is going to be north, okay? Electron moving north encounters a magnetic field. So here's the direction north, that is the motion, yeah? And then the direction of the magnetic field is basically towards east, yeah? So what is the direction of the magnetic force here? Sorry, no, I'm holding this one wrong here. So this is the direction of the force on a proton, this is an electron. So motion is upward, north, and then this is the direction of the magnetic field. So what is the direction of the force or magnetic force on an electron? Can I say into? No, don't forget, if it is into, that is for a proton. What we have is an electron, so an electron is the back of the hand, so it is going to be out of the page here. But if we're going to use north, south, and all that, of course, you can say upward here, because remember this, that is north, yeah? So if I do my hand like this, of course, then this out of the page, it is going to be upward in this case, yeah? So of course, we can say upward, and that is basically B here, okay? That is how you can do this one. All right, and then the magnetic force effect by electric charge in uniform magnetic field is maximum. When is it maximum? It is maximum when the direction of the magnetic field, or you can say the angle between the direction of the motion of the electron or moving electron and the direction of the magnetic field must be 90 degrees, because it has to be sine 90, so we get maximum magnetic force. Okay, and then what about in question 6 here? Question 6 is also interesting. Says what? In the figure, find the direction of the magnetic force on a proton moving with a velocity, let's say v, through a magnetic field as it is shown in the picture here. So watch this. This is the direction of the v, which is out of the page. This is the direction of the magnetic field, which is, let's say, up the page. What would be the direction of the magnetic force here? So once again, you could do something like this. Yeah, this is out of the page. You can see my thumb. It is out of the page. Okay, let me hold the pen correctly. So this is out of the page. This is the direction of the magnetic field, which is upward here. What would be the direction of a magnetic force on a proton? Yes, if it is a proton, don't forget, guys. So it is going to be your palm, yeah? So basically upward, and this is out of the page, so it is going to be, you can say, towards the left of the page, if that is the case, yeah? So up the page, down the page, to the left of the page, to the right is going to be the left of the page in this case. Okay, take a look at question 7. That is a recent WZADI question. What does it say? It says, suppose we have 4 charges, that is Q1, 2, 3, 4. Each is moving in a circle path in a magnetic field, as in the figures. Which of them is positive charge? Remember this, we're just going to align our hand the same way as the pictures are telling us. If the force is directed, let's say, based on the using right hand rule, if it agrees with that, and if the force is towards the let's say towards the center of the circle, in this case we can say this is correct. If not, it is incorrect. Okay, because we said whenever there's a charge moving, there's always a force perpendicular, let's say, towards the center, yeah? But remember this, it has to be a correct alignment with the directions, otherwise it will be incorrect. So take a look at the first one here. Okay, so the first one says, if we do this one here, it says the charge is moving upward. The magnetic field is into the page, yeah? So the charge is moving upward. If that is the case, there will be a magnetic force on a proton, positive charge, which is going to be towards the center of the circle. So this charge must be positive, because if it is positive, it gets a force, which is, remember, the palm of the hand here, which is going to be towards the center. Now let's take a look at the second charge here. The second charge says the magnetic field is out of the page here. So you can see this is the direction of the motion, but the magnetic field is out of the page. So I'll have to do something like this, yeah? So this is the direction of the motion. Can you see that? Upward. And this is the direction of the magnetic field, which is out of the page towards you. So a magnetic force on a positive charge will be moving to the left, not to the because remember, this is going to be left, so here is going to be the direction of the force on a positive charge. But this diagram, it tells you that it is directed towards the center. If that is the case, then this is the force on a negative charge. So Q2 must be negative, not positive. Okay, what about Q3 here? Okay, the magnetic field, again, it is into the page, but the direction of the motion is basically downward, yeah? So I'll do something like this. So once again, you can see the back of my hand is towards the center, but the back of my hand is for negative charge. That means this is also negative charge. Okay, what about the fourth charge here? So the direction of the magnetic field, it is out of the page. Okay, what about the direction of the motion? The direction of the motion is downward, you can see. So out of the page, downward here. So there is a magnetic force on a positive charge, the palm, it is into the circle. So we can say Q4 is a positive charge as well. So what are the charges that are positive? Of course, that is Q1 and of course Q4. So we can, which one of these are Q1 and Q4? That is option A here. So of course, this is how you can tell which one is which. So best of luck trying to practice this more and more. Okay, now let's solve a few questions, yeah? It says a proton is moving east, experiences a force of this much upward due to the Earth's magnetic field. At this location, the field has a magnitude of 5.5 times this much towards the north. Find the speed of the particle. Okay, now let's solve a few questions because we're done. We're almost like done with the direction. We talked about direction too much, and I hope it was worth it. If not, then I'll be regretting that, to be honest. But I hope you understood well enough so that I feel I've done something useful. Okay, so take a look here. It says a proton moving and all that. We talked about the direction. So let me just redo this real quick. We have a proton, okay, so a positive charge. It says experience a force. So we have a force. We can say magnetic force, which is basically 8.8 times 10 to the power negative 19 Newton. That is for this upward. We don't care about the direction at this point here. That is why we don't care about the upward or the direction here. We have the magnetic field strength, which is B basically equals to 5.5 times 10 to the power negative 5 Tesla. Okay, the strength of the magnetic field. Find the speed of the particle, yeah? So V is unknown. But remember this, since it is a positive charge, it is one charge, a proton, yeah? So the value for this charge, remember, the magnitude for this charge is 1.6 times 10 to the power negative 19. We're not talking about whether the charge is positive or negative. We're just talking about the magnitude of this charge in here. So can we find the speed of the particle? Yes. Okay, so once again, we'll say, okay, let's do this. We'll say magnetic force. You do know that. What is the equation? Remember, magnetic force on a charge, yeah? We'll say QVB, okay, sine theta. But watch this, guys. Do I need this part? You tell me this, because it tells you this, okay? Proton moving east, experience the force of this upward, let's say. So there is, these two basically are perpendicular to one another. So we can say that this part equals to sine 90, that is 1. That is one thing you, for example, perhaps if you ever wanted to know. But let me tell you something else. If it doesn't talk about the angles, or if angles are not given, so that means these two are more likely, most of the time, is perpendicular to one another. It tells you, of course, it gives you enough information so that you can tell whether it is perpendicular or not, and then of course you can do your calculation. When do you, for example, when you don't have to use this, if it tells you that the charge is moving parallel to the magnetic field, then this force will be 0, and of course you don't need any calculation as well in that case. So just remember, if angles are not given, it is more likely that you are going to use F magnetic equal to QVB. But you have to be very careful, just in case if it says the direction of the movement is parallel to the direction of the magnetic field. If that is the case, then the whole thing becomes 0. All right, so this part is 1 now. So we won the velocity, yeah? So of course, make this velocity the subject here. So velocity equals to F magnetic over QB, yeah? And then of course, substitute the numbers, plug in the numbers, and of course, you will get the answer correct. So the force is 8.8 times 10 to the power negative 19. Yeah, it is negative 19. Okay, that is the force. What about the charges? Basically, will be given. If not, you try to, okay, just memorize this once and for all. In terms of the charges, by the way, the charge of electron and proton are the same in terms of magnitude. Okay, so 1.6 times 10 to the power negative 19 multiplied by the magnetic field strength, which is 5.5 multiplied by 10 to the power negative 5 Tesla. And of course, you do the math, you'll get the magnitude of the velocity, that is meter per second here. By the way, it doesn't ask for the direction, so we don't have to worry about the direction here. Okay, moving on. That is basically, it was for this one here. Okay, moving on to the next question. In this question here, it talks about, or it wants the direction here. Okay, so it says, if an electron in an electron beam experiences a downward force, which is basically this much, while traveling in a magnitude of this much west, what is the direction and the magnitude of the velocity here? Okay, so basically this is pretty much the same with the other question, except that here it asks for the direction as well. So I'm not going to do or repeat the math for the first part. I'll just write the equation, you do the math, and then, but what I'll do here, I'll tell you how you can find the direction here. So basically, once again, let's move this a little bit. Okay, so magnetic force we can say equals to QVB, yes? Okay, so you can see that you don't need sine theta because that is basically perpendicular to one another. Okay, so maximum you can say, so V equals to F magnetic over Q times Q times B. Okay, magnetic field strength. Then of course, plug in the numbers, you'll find the answer meter per second. That is for the magnitude of the magnetic force. What about the direction? Because it says find the direction and magnitude here. So we found the magnitude, let's assume. What about the direction here? Remember this. So it talks about this one here. So the direction that we are given is basically, we have these directions, north, south, east. Okay, perhaps we have two north here. North and south, east and west, okay? So this is the direction. But remember this, it tells you that the magnitude of the magnetic force is basically downward here. So if this is, we can say downward, downwards. And of course, these are perpendicular to one another. So if I do this, remember we have an electron here, by the way, okay? So what would be the direction of the velocity in this case? So if we redo this one, electron experiences a downward force. So this is a downward force, we can say F on an electron, or magnetic force on an electron here. Let me rewrite this one so it doesn't confuse you. Magnetic force on an electron, you can say, which is downward. And then the direction of the, or you can say the direction of the magnetic field is towards west here. So B basically is towards west. So what would be the direction of the velocity here? Okay, so once again, remember this, because we're talking about an electron, so keep an eye on the back of my hand, let's say. So the force is downward, the magnetic field is basically towards west, that is the magnetic field, let's say. But if I do it this way, that is the direction of a magnetic force on a proton, yeah? So I'll have to flip my hand basically. So I'll have to do it this way because there is a magnetic force on the electron here, you can say. And this is the direction of what? The direction of the magnetic field strength, let's say. So in this case, my thumb would point basically north, okay? But in order to understand this better, I'll do this one just for now so that you understand this. So for example, because we're talking about north, south, east, and west, so basically this side, the tip of my finger represents north, the back of my hand basically, not the back of my hand, let's say this part of my hand points south, this is east, and this is west, yeah? If I do it upward, perhaps it makes more sense. This is going to be north, let's say, this is going to be east, west, and of course the bottom of, let's say, my arm is going to be representing south here. But once again, keep an eye on the back of my hand because we have an electron here. So if I do it again, okay, remember magnetic field, okay, that is strength, direction, and this is the magnetic force here, so this is the direction of the motion here, which is towards north here. If I flip my hand this way, perhaps it makes more sense because that is west, and this is the